Good morning, dear students. Today I am going to discuss about the famous Onsager theory of electrolytic conductance that is considered as the modified theory of electrolytic conductance especially deals with the strong electrolytes. So that theory is generally known as the theory of strong electrolyte theory of the conductance of the strong electrolytes. Okay, so let me start. You have to first going through the postulates of the theory first, then you have to go through an equation. There is no need for you to derive the equation. It's a very large, big equation. That equation is to be derived for your MSc class only, for MSc syllabus only. In your BSc syllabus, you have to identify the various two important force term, electrostatic force term that will going to diminish the speed or the ionic mobility of the ion. That aspect is to be discussed, and you have to write an equation. You have to study an equation for the equivalent conductance of the electrolyte for a particular concentration. For in the case of a strong electrolyte, by accounting the various electrostatic force term. So once again, I wish to say the fact is that the need of this theory, okay, that is the main disadvantage of the or limitation of the Arrhenius theory is that it just omitted, okay, it just neglected the change in the speed of the ion or ionic mobility arising from the electrostatic force term during the dilution of the solution. He said that the electrical conductance of any electrolyte depends only on the number of free ion present in the solution, and he did not account the change in the ionic speed of the ion that arising from the decrease in electrostatic force of reaction which occurred during the dilution. What Debye and Haeckel, along with in association with the Onsager, did is that they accounted the effect of the electrostatic force term on the ionic mobility, okay, that occurred during the dilution, and thus the variation of the ionic mobility that occurred during the dilution, okay, that arising from the decrease in the electrostatic force term was accounted, and thereby they modified the electrolytic conductance theory. So, based on the new theory, we have to say that the electrical conductance of any electrolyte in solution, especially the strong electrolytes, depends not only on the number of free ion present in their solution, but also on the variation of the ionic mobility which arise from the change in its electrostatic force of attraction to various electrostatic force term exists in the solution that occur during the dilution of the solution. And that equation is known as the Debye-Haeckel-Onsager equation. And the postulate is that the essential postulate the postulates of, actually it has two parts. One is Debye-Haeckel theory, and second is the addition that is given by the Onsager. Hence the theory is known as Debye-Haeckel theory and the equation is known as Debye-Haeckel-Onsager equation. Okay, we can consider this same together, Debye-Haeckel-Onsager theory and the corresponding Debye-Haeckel-Onsager equation. The essential postulates of this theory as applied to strong electrolyte. Okay, supply to strong electrolyte. The postulates. All strong electrolytes. One, all strong electrolytes are completely ionized in all dilution in their solution. That is the first postulate. All strong electrolytes, all strong electrolytes are completely, CIMPAT, completely ionized. All electrolytes are completely ionized in all dilution, or all concentration, or at all concentration in the solution. So this is the first postulate. So all the strong electrolytes are almost completely ionized in all the dilution or at any concentration in the solution. And the second important postulate is that due to the electrical attraction, each ion is surrounded by an ionic atmosphere of opposite sign than that of its own ion. So due to the electrostatic attraction, a particular charged ion, the neighborhood of a particular charged ion, there is a probability of a greater ion of opposite charge, opposite sign than that of its own. And this results in an ionic atmosphere surrounding a particular ion. So that is an important postulate, that due to the electrostatic attraction between the positive and negative ion, there are on the average in the neighborhood of any ion, there is a greater charge density of opposite ion than its own ion, or each ion is surrounded by an ionic atmosphere of opposite sign. That is important postulate. Due to the electrical attraction. That's the second postulate is predicted the existence of an ionic atmosphere of opposite sign around each ion due to the electrical attraction. Each ion is surrounded by an ionic atmosphere. Surrounded, because the shape of the ionic atmosphere is almost spherical. Each ion is surrounded by an ionic atmosphere of opposite charge, opposite sign. So this is called the charged ionic atmosphere. The accumulation of the greater charge of opposite sign in the neighborhood of any ion in the form of a sphere is called ionic atmosphere. That is called ionic atmosphere. So that means surrounding in the neighborhood of each ion there is a greater probability of greater ion of opposite sign than its own ion, or we can assume that each ion is surrounded by an ionic atmosphere of opposite signs. For example, a positive ion is surrounded by greater number of negative ion, and a central negative ion is surrounded by a greater number of positive ions. So this is an example of this charge density. Like this, negative, like this. This is almost an example of a charge density. That means each ion is surrounded by as an ionic atmosphere of opposite charge density, and this is called ionic atmosphere. Okay. Then this actually gives us that is electrostatic attraction. This is called this leading to an electrostatic attraction process that is presented by a particular ion by charge density. So what you have to remember is that each ion in the solution is surrounded by an ionic atmosphere of opposite sign, and this ionic atmosphere gives rise to an attractive force towards the mobility of the ion, or it will that is impart a retarding force on the speed of the ion, or ionic mobility of the ion. Then the separation next is, you know, that the effect of dilution on diluting, on increasing the electrolytes more and more by adding, or on diluting, the effect is that the separation of the ion takes place, and for that a work is required, or energy is required against the electrostatic force of attraction. Okay. On dilution, the separation of ions takes place, and a work or energy is required against the electrostatic force of attraction. So what I want to mention is that, you know, that during the dilution, the electrical conductance of the solution increases. It is due to the separation of the ion from the electrostatic force of attraction, thereby leading to the increase in the ionic mobility. Okay. So dilution in the solution, the separation of the ion from one another takes place, and a work is required against the electrostatic force of attraction for the separation, that leading to a greater mobility, and hence greater conductance. Then 4. The increase in the conductivity, okay, the fourth assumption is that the increase of the conductivity of a strong electrolyte in solution during the dilution is due to the increase in the ionic mobility arising from the reduction in the electrostatic force of attraction, and not due to the increase in the number of ions. So, for the assumption, the increase of the conductance of the strong electrolyte, we are dealing with the strong electrolyte, is due to the increase in the ionic mobility, okay, arising from the reduction in the electrostatic force. Okay, electrostatic force. That is the situation. So, the increase of the conductance of the electrolyte, the strong electrolyte, the solution is not due to the increase in the mobility of the, not due to the increase in the number of ions, but only due to the increase in the ionic mobility, which arises from the reduction in the electrostatic force on dilution. Okay, that is, we have seen that on increasing the dilution of the solution, we have seen a gradual increase in the electrical conductance, the molar conductivity of the electrolyte, and that increase is not due to the increase in the speed of that is number of ion, it is due to the increase in the speed or ionic mobility of the ion that arising from the reduction in the electrostatic force that occurred during the dilution. So next we have to identify the nature of the electrostatic force. Okay, that is finally at infinite dilution, at the infinite dilution. Okay, that is the stage of complete dilution. At infinite dilution, the ions are randomly are distributed randomly. So the ions are far away. So that completely random, the distribution. At infinite dilution, the ions are distributed in a completely random manner. Distributed in a completely random way. In a random manner, randomly. So completely randomly. So that they are far apart. So they are far apart from each other to exert attraction. So they are completely away from the electrostatic force of attraction. They are completely free from the force of attraction at the infinite dilution because the distribution of the ion is random. Okay, that stage is actually an ideal stage at which the lambda become lambda infinity or lambda 0. Okay, so there is no attractive force that exerting on the mobility of the ion. That is an ideal condition at which we can say alpha now becomes strictly equal to 1. Okay, this condition, at that ideal condition, the alpha of a strong ray strictly become equal to 1. Then, and sixth term, we have to identify the electrostatic force. The electrostatic force acting between the opposite charged ion in their solution is governed by the inverse square law. That is, F is equal to Z1 Z2 E square by D square by D. This equation. So, the electrostatic force of attraction that exists acting between the positive ion and negative ion present in the solution of strong electrolyte is given by the equation that is Z1 Z2 E square by D square by D, where Z1 and Z2 are the valence of the two ion, positive and negative ion. Okay, the valence of the positive or negative ion, there is Z plus and Z minus. Okay, positive Z plus and Z minus, and E the charge, magnitude of the charge. Okay, that is coulombs. 4.82 into 10 raised minus 3 SU or 1.766 equal to 10 raised to 9. Okay, something coulomb. And D, small d is the distance or separation, distance between the ion. So small d is the distance that separates the ion from one another. So greater the distance, lesser the attractive force, or smaller the distance, greater will be the attractive force. So that is called inverse square law. So but the force term is directly proportional to the product of the charge and inversely proportional to the square of the distance. And also it is inversely proportional to D, the capital D, that is the dielectric power or the dielectric constant of the solvent. D is the dielectric constant. So this equation says that the electrostatic force of attraction is greater in a solvent of lower dielectric constant because the electrostatic attraction force is inversely proportional to the dielectric constant. So lesser the dielectric constant, greater the force. That means the electrostatic force of attraction is become more powerful. One, there are three factors that will affect the electrostatic force of attraction in the case of strong electrolyte in their solution. One is greater the valence of the ion of the electrodes, greater the valence of the ion of the electrolyte, greater will be the electrostatic force. So greater valence of the ion, then lesser the distance and lesser the dielectric constant of the solvent. So in a solvent of lesser dielectric constant at a distance of smaller distance and in a ion of greater electrical charge, or greater valence, the force of attraction, the electrostatic force of attraction is greater. So that is the situation. So again, the electrostatic attractive force is governed by inverse square law, according to which it is equal to Z1 Z2 E square by D square by D, where Z1 Z2 is the valence of the positive and negative ion and E is the magnitude of the charge, and D is the distance of the separation between the positive and negative ion, and the capital D is the dielectric constant of the solvent. So in the D, when capital D, the dielectric constant become lower, so F is inversely proportional to dielectric constant of solvent, and this F is inversely proportional to the square of the distance between the separation of the ion, and F is directly proportional to the product of the valence of the ion. So the force of attraction is powerful when a solution of lower dielectric constant at a smaller distance for the ion of greater valence. So this is the theory. Finally, that is, this is generally called Debye and Haeckel theory, and later Onsager, another young scientist at the age of 22, you remember, at the age of 22, he put forward, he accounted that in the electrolyte solution, for the electrolyte, strong electrolyte in the solution, he identified the two different attractive force that exist in the solution. Or the scientist Onsager identified two different attractive forces in the solution of strong electrolyte. So actually, the nature of the attractive force that will drag or that will reduce the speed of the ion is actually accorded by the scientist called Onsager. Okay, there are various factors. You know that the attractive force summarized due to one. It may be the charge density, electrical charge density of opposite side. Okay, that is a complicated thing. Later, the Onsager identified two different types of attractive forces operating in the solution of the strong electrolyte, and they are, hence that theory is called the Debye-Haeckel-Onsager theory. So Onsager identified the two attractive forces. One is the relaxation force, or otherwise called or asymmetry force. Okay, one is relaxation or asymmetry force term, and the second is the electrophoretic force term. Okay, you have to see what are the two forces. Then only our discussion will get complete. So let me pass on to these two forces. So in addition to, that is later, and I think in 1922, Debye and Haeckel postulated this theory earlier, but later in 1922, the young scientist Onsager identified the actual attractive force that is operating in the solution of the electrolyte, and that will drag or reduce the ionic speed or ionic mobility of the electrolyte. These two attractive forces are, one, the relaxation force or the asymmetry force, and second is the electrophoretic force. Okay. First we have to discuss the relaxation force. The relaxation force that I already mentioned. In the case of a strong electrolyte in a solution, that is each ion that is considered central ion, each ion in the solution is surrounded by an ionic atmosphere of opposite sign. Okay. Each ion is surrounded. Okay. The nature of the ionic atmosphere is that it is almost spherical. Okay. Each ion is surrounded by an ionic atmosphere of opposite sign. In the absence of an applied electric field, the ionic atmosphere is almost spherical. So, the ionic atmosphere, okay, each ion, that is called a central ion. Okay, the ion of interest is central ion. That is we are going to account. It's undergoing movement or migration during the application of electric field. That ion is called a central ion. That each ion that is considered a central ion is surrounded by an ionic atmosphere, and the nature of the ionic atmosphere is completely spherical. It is spherical. The geometry of the ionic atmosphere is completely spherical. That is also very important. The ionic atmosphere is spherical in the absence of the electric field. When we apply under the influence, when electric field is applied, or under the influence of the electric field, when electric field is applied or under the influence of the electric field, okay, influence of the electric field, okay, the situation changes. Under the influence of the electric field, the symmetry, the spherical symmetry of the ionic atmosphere is lost. It is spherically symmetrical. The symmetry of the ionic atmosphere is lost. The spherically symmetrical. Spherically symmetrical. The spherical symmetry of the ionic atmosphere is lost, that I wish to say. So under the influence of the applied electric field, the spherical symmetry or spherically symmetrical ionic atmosphere, the spherical symmetry of the ionic atmosphere is lost, because under the influence of the electric field, the ion try to move towards one direction. Let it be in the right direction. Let me say that the ion is trying to move in this direction, towards front. When the ion try to move towards the front, towards right, okay, towards right or towards the front, the ionic atmosphere, they are opposite sign, they tend to move backward. They tend to move towards backward direction because of the electric charge density. So that the ionic atmosphere surrounding that spherical symmetry is lost, and it is now changed in this fashion. So under the influence of the applied field, when the ion tend to move towards right, towards the front direction, the ionic atmosphere with this, okay, is tend towards backwards, okay, like this. Or there is a greater accumulation of charge density in the back than it is in the front side. So there is an accumulation of great charge density, there is opposite ionic atmosphere charge density in the back than in the front. That is the situation. Okay, you think again. So, and when we apply an electric field, the central ion tend to move towards rightwards or towards the front, but the ionic atmosphere tend to move towards the opposite direction, that is towards the back side. So there is a chance. So at this stage, the spherical symmetry of the ionic atmosphere is lost, and there is a greater accumulation of the opposite charge density just behind the ion than in the front. Okay. And the ion require a time to build its own atmosphere, a new ionic atmosphere on the, again around it. It requires time. There is time lag is there. As move rightways, it has to build it. It has to build its own new ionic atmosphere around it, but it requires a time, or a time lag is there to construct an ionic atmosphere on the direction of the motion. During this time lag, the opposite charge density or ionic atmosphere will offer a dragging force, will produce a dragging force on the mobility of the ion moving towards front. Thereby, its velocity movement is reduced or speed is reduced. And this dragging force that arises from the asymmetry or the charge density or ionic atmosphere is called the asymmetry effect, or that arising from the time of the relaxation, time lag arising from the construction of the new ionic atmosphere. This dragging force is known as relaxation force or asymmetry force. So I hope you are understood the facts why it is called this way, in this fashion, asymmetry force or relaxation force. That is, normally the nature of the ionic atmosphere surrounding the central ion is almost spherically symmetrical. Okay, in the absence of the electric field. When we apply the electric field for the electrical conductance, the ion tend to move towards the front side, towards the right, so that the ionic atmosphere of the opposite sign tend to move backwards towards the back side. So the spherical symmetry of the ionic atmosphere is lost, so that there is a greater accumulation of the opposite charge density just behind the ion than in the front. Okay, that means the symmetry of the ionic atmosphere is lost, that will become asymmetric. Okay, that become asymmetric. The ionic atmosphere now become asymmetric. The next thing is that the ion has to build a new ionic atmosphere of its own on the direction of the motion, but which require a time, or a time relaxation is there. It want a time, or it has a time lag for building the new ionic atmosphere. This time lag is called time of relaxation. So during this time of the relaxation or the time lag, what actually happening is that the oppositely charged the ionic atmosphere just behind the ion, greater charge density just behind the ion, or that arising from the asymmetry, offer a dragging force or the mobility of the ion. Thereby the mobility of the ion get retarded, the speed of the ion get retarded. This retarding force or the mobility or the speed of the ion, okay, that arising from the asymmetry of the ionic atmosphere, which in turn arising from the time of relaxation or time of that is called asymmetry force or time relaxation force. The after effect, the net effect of this attraction force is that the speed of the ion is reduced, so that the electrical conductance get diminished, get reduced. That's the situation. Okay, what is the expression for this time electrostatic force term? It's a very big term. I am not going to write this. Finally, I will write. So you understand the fact. That's it. Actually, suppose you want to know the term, I will write. It's a very huge term. The relaxation force term or the asymmetry force term is given by epsilon cube. Is also very good. That's epsilon cube is a die. Okay, kappa omega V by 6d kT. This equation. But this charge, this is the valence, this is the a term representing the ionic atmosphere, kappa, d by length, omega, a term connected to time of relaxation, V is the applied voltage, D the dielectric constant, K the Boltzmann constant, and T is the temperature. Suppose you want to know the equation, you can write this. The relaxation force or asymmetric force is given by, force attractive force is given by, okay, that is epsilon q is I kappa omega V by 6d kT, where this charge, magnitude of this valence, this is kappa, that d by length, or that is called magnitude of the ionic atmosphere, omega the time of relaxation, V the applied voltage, D the dielectric constant, K Boltzmann constant, T is the temperature. Okay. The rest you have to express the second force term. The second force, the retarding force that we have to discuss is second is the electrophoretic force. Electrophoretic force. Okay. That is when the central ion, okay, when we applied, that's already mentioned, the central ion surrounded by an ionic atmosphere of opposite sign, which is almost spherical under, if there is no field, okay, it's almost spherical. Under the influence of the applied fields, when we applied fields, applied electric fields, so when the central ion is attached to large number of solvent molecules, similarly, the ionic atmosphere is also attached to large number of solvent molecules. That's the situation. The situation is so much such that the central ion is associated with the large number of solvent molecules, and the ionic atmosphere is also associated with a large number of solvent molecules. Okay, this is a situation. So under the influence of the applied electric field, when the central ion with this attached water molecule move towards right, the ionic atmosphere along with this attached solvent molecule will try to move in the opposite direction, that is towards the backward direction, towards left. This is the situation. Okay. Like this. This is the situation. So, under the influence of the applied electric field, when the central ion with its associated solvent molecule tend to move towards the right or towards the front side, towards the right, the ionic atmosphere with the opposite charge ionic atmosphere with its attached solvent molecule will tend to move towards left or towards the back side. This tendency, moving tendency of the ionic atmosphere with its, along with the solvent molecule, will create a stream, will create a driving force created by the stream or the movement of the solvent molecule, okay, which is equivalent to the driving force that is arising from the frictional resistance of the solvent and also from the viscous resistance of the solvent. So both driving force now come into play. Okay, as the central solvent molecule move towards the right, okay, at the same time the ionic atmosphere with its associated solvent molecules, not ionic atmosphere alone, the ionic atmosphere with its associated solvent molecule tend to move towards the opposite direction, towards backward direction or towards the left, and this will create a dragging force just like a stream which will offer the movement of the central ion. And this dragging force that arising from the frictional resistance of the solvent and also from the viscous resistance of the solvent, that are called electrophoretic force term. And this electrophoretic force That is the movement of the ionic atmosphere with its associated solid molecule will offer a frictional resistance on the flow of central ion towards the front direction, opposite direction, and thereby the movement is reduced and hence the conductivity is also reduced. This driving force which arising from the frictional resistance of the solvent and the viscosity of the solvent resistance is called electrophoretic force term, and that is given by the equation. Okay, that also depends on the viscosity, and that is given by the equation viscous resistance, that is given by electrophoretic force term, that is F is equal to epsilon I is a di kappa KIV by 6 pi eta. Suppose anyone want to study this equation, you can remember this equation. The electrophoretic force term is epsilon I, charge of the ion, magnitude of charge of the ion, is a di valence of the ion. Kappa is the magnitude of the ionic atmosphere, d by length. Okay, some term representing the ionic atmosphere. Ki is the coefficient of the frictional resistance of the solvent. V is the applied voltage, and eta is the coefficient of the viscosity of the solvent. So that is the situation. Okay. Now that is the equation now become like this. Now we have to account at these two factors. But actually, Onsager accounted these two force terms. Okay, the scientist Onsager accounted these two attractive force terms, and he modified the equation suggested by the Debye-Heckel theory, or along with the Debye-Heckel theory. Onsager incorporated these two force terms, and collectively they derived an equation. Okay, they deduced an equation for the conductance of the electrolyte, strong electrolyte in the solution, and that is given by the molar conductance of the electrolyte. The molar conductance of the electrolyte, lambda m, is equal to lambda 0 m minus a plus b lambda 0, a plus b lambda 0 into square root of c, where the constant A is equal to, 82.4 divided by dt raised to half into eta, and constant B is equal to 8.20 into 10 to the power of 5 divided by dt raised to 3 by 2. Okay, where so the molar conductance lambda 0 m. Okay, lambda m is equal to lambda 0 m, the molar conductivity of the electrolyte at any concentration C is equal to molar conductivity at infinity or zero concentration dilution minus a constant A plus B lambda 0 m into square root of C, where the term A is called the electrophoretic attractive force term. The constant A stands for the electrophoretic attractive force term, that is 82.4 divided by dt raised half into by eta, where eta is the viscosity, d is the dielectric constant, c is the temperature, and the V stands for the second force, that is the relaxation or asymmetric force term, that is 8.20 into 10 to the power of 5 divided by dt raised to 3 by 2. So this is an equation of a straight line. This equation says that the molar conductivity of any electrolyte is lesser than the molar conductivity at infinite dilution, depending on this electrostatic attractive force term, and also it is directly proportional to the concentration of the electrolytes. That you have to remember. So depending on the concentration of the electrolyte, it is this lambda 0, lambda cm, molar conductivity of electrolyte at any concentration is lesser than lambda 0 m by a factor of this, that is, as it is directly proportional to the square root of the concentration. So greater the concentration, greater will be the attractive force term, and therefore lesser will be the conductance of the electrolyte at a particular concentration. As the concentration decreases, as the concentration of the electrolyte solution decreases, gradually the A and B term diminishes, thereby increases the ionic speed and thereby increases the molar conductivity. This term diminishes. Okay. As the concentration decreases, correspondingly A and B term also decreases. Okay. Thereby that is lambda Cm increases. That is the situation. So that the plot of this is an equation of a straight line. This is an equation of a straight line. That is, if we plot lambda Cm versus square root of C, for most of the strong electrolyte, this is found to be a straight line. This is found to be a straight line like this. This is like HCl, this is for KCl. Okay. And a slight variation is obtained. Okay. A slight change is occurred at a very high concentration. You know in England, because the discussion is not required for you. Anyway, what you have to remember is that this is an equation of a straight line. So we plot the lambda m versus square root of C. The result is a straight line, and the slope of this straight line gives a plus b lambda 0 m. That's the thing you have to remember. The slope this gives, this is a negative slope. The plot of lambda m versus square root of C is a straight line with a negative slope, and the slope of this equation gives a plus b lambda 0 m, from which we can calculate A and B, the attractive force term. We can get the information about the magnitude of the A and B force term that vary with the different electrolyte. It is different for HCl, different for KCl. It is almost same for KCl and HCl, NaCl. And it is very much different for copper sulfate, magnesium chloride, etc. As the ion electrolyte become more and more valence ion, okay, that is univalent, unidivalent, divalent. Okay, all these cases. But is actually, as the number valence of ion increases, greater will be the magnitude of the A and B that you are to study. So time being, what I wish to say is that this is an equation which shows the variation of the molar conductivity of the electrolytes, the dilution almost completely. Or we can say that this is a good equation. This is an equation that is obeyed by most of the strong electrolytes. The conductance, the variation of the conductance behavior of the strong electrolyte with respect to dilution can be explained by means of this equation. So that we will get a straight line plot with a negative slope. Okay, that is according to this equation. So when we carry out the experiment, and substitute in this equation the values and then plot graphically, the result is a straight line, shows that this equation is valid for most of the strong electrolyte. This is especially valid for all the univalent and the unidivalent, but the case of bivalent, there is slight discrepancies, a deviation is observed. Okay, that all aspect will be discussed for a MSc class. So from the slope you will get A plus B, the attractive force. So thank you very much for listening to me in the class. I hope that you have understood the class very well. So I am going to wind up the class. Next class we will discuss about the ionic mobility, the speed of the ion. Okay, the parameter represents speed, ionic mobility, transport number, connection with the ionic mobility, and method for determining the transport number. According to your syllabus, we have to discuss two methods. One is moving boundary method and other is a torque method. That may be asked as an essay. And this also will be asked as an essay. So you try to concentrate your study much on this D-Behakel equation. It will be asked for your examination as an essay. Okay, thank you very much.